This is 2020 European Girls Math Olympiad problem number 3, and here is a view of this problem. We are given a convex hexagon, and these three angles A, C, and E, as well as those three angles B, D, and F, they are all equal in that fashion. When I say angle A, what I really mean is angle FAB for that convex hexagon ABCDEF. Well, knowing that the angle bisectors of AC and E are concurrent at a point, say P for instance, at P, show that the interior angle bisectors of BD and F must also be concurrent, say at a point, for instance, Q. Before I begin the solution to this problem, I want to start with just two quick observations. They are not even lemmas, I think, observations. Just two quick observations, and then we can directly start the solution. Actually, let me think about it. Three observations. Okay, the first observation is the following, which is, I think it's an obvious result. So if you have an angle and then an angle bisector here, that's an angle bisector. Any point that you pick on that angle bisector, if you check the distances from that point on the angle bisector to the two rays making that angle, so this is XY, that's the point P on that angle bisector, then necessarily PX is equal to PY. Y by symmetry, or Y by what do you call it? Congruent triangles, right? So triangle AXP and AYP, they are clearly congruent triangles, and boom. So yeah, there is nothing to prove. Awesome. So that was our first observation. The second observation is a trick that I like a lot. I think it's called Viviani theorem or Viviani lemma. Viviani's theorem or lemma, doesn't matter. It's a simple result, I mean. And it is the following. If you have an equilateral triangle and you want to calculate the distance, so triangle ABC for instance, and we have a point P inside that triangle, and if I draw perpendiculars to the three sides of this equilateral triangle, it turns out that the sum of these distances, let me call it as PX plus PY plus PZ, apparently this comes out as the altitude, let's call it H, of triangle ABC, the altitude of triangle ABC. And the proof is rather straightforward, actually. It's just a quick trick, and it is the following. So again, triangle ABC is given as equilateral, right? It only works if you have an equilateral triangle. So I can draw a parallel line at B, so at P to side BC. So this is parallel. Then I will draw another parallel line to AB this time. So this line through P is parallel to AB. There you go. Then it is clear that distance PY is the same thing as the following distance, starting from that vertex all the way down here. Why? Because if you label these new points as, say, I don't know, let's call them D and E, clearly triangle DPE is also an equilateral triangle. So as a result, in an equilateral triangle, all three altitudes, they measure the same length. So if you label that point here as Q, necessarily PY is equal to DQ. Do you guys see that? So therefore, so that's what I needed to prove, question mark. So if you start with PX plus PY with the left-hand side, let's try to prove that you will achieve, you will get to the altitude in the end. So Px plus Py plus Pz is what? That's the claim, and this is the proof. All right, so, well, Px, let's just keep it for the time being. Py, replace it with qd or dq, let's call it. And finally pz. For pz, I can do the following. I can yet draw a new, another parallel line, though this time I won't do that line through, well, actually I can if you guys want it. Okay, let's just do it. The last remaining parallel is this one through the point P as parallel to side AC. Again, by that same trick, PZ is just an altitude in that tiny triangle. I don't want to even label the points, but okay, let's label this one as a U, this one as a V. Clearly, UVP is also an equilateral triangle, and PZ is an altitude of that triangle. Alternatively, another, well, actually, you know what? We didn't even have to do this. I should have rather drawn a parallel line through D. How about that? This is even better. So if you draw a line parallel to BC through D, that tiny triangle here, check this out. PZ happens to be the altitude of that triangle as well, simply because I can just shift this distance. These distances are all, because those two lines are parallel, AB and DP are parallel. So namely, so this is equal to that distance, that perpendicular. But wait, triangle A, whatever you call this one, W, let's call it W, AWD is an equilateral triangle. And this is an altitude in that equilateral triangle, namely, so this is, we might as well just draw the other altitude. Do you guys see that? And as a result, what's interesting is that we have for this triangle ABC now 3 segments. Let me just make it slightly larger. So for that tiny triangle, we have that distance over here, and then we have this distance, and then we have this distance. Clearly, they add up to the whole altitude, right? Because you have all these 3 layers of parallel lines, BC, PE, and WD. They are all parallel lines. So this PX, I think we called it, carries over here, DQ carries over here, and then we had also this last one as well. They add up to H basically. Yeah, so that was the claim, and we have just proven the claim that this Viviani theorem or Viviani lemma, whatever you call it, that the DQ and whatever you call that tiny point here at the bottom, what should we call it? AT, for instance. Yeah, these 3 should add up to H, basically. All right, so we have proven Viviani's theorem as well. Now, last result is the following. It's a very cool result, and it is the following. It's as it relates to our picture, to the givens in our in the problem at hand. So if you have a hexagon, A, B, C, D, E, F, I should say, then we are told in the problem statement that angle A is equal to angle C, which is also equal to angle E. And similarly, angle B measures the same as angle D, which measures the same as angle F. Now, the trick is the following, so we can think about that. We can just go ahead and extend the 6 sides of this hexagon, and as a result, we will get a star shape. Well, the Star of David in this case. So we have this, that, and lastly this. Now, something very interesting happens here, right? So for instance, I can call these points as X, Y, and Z, and then the remaining 3 points are P, Q, R, for instance. I claim that, so this is the third observation, triangle XYZ is equilateral, as is triangle PQR. And it is just such a simple angle chase. So for instance, this red angle here and this blue angle, so such that, so you have this angle over there, whatever that is. Now when you compare it with this angle also is inside triangle ABP, but then you have this outside red angle and blue angle, so therefore this angle should measure the same as angle X. Do you guys see that? Similarly, this angle on triangle BCY, a blue angle here, a red angle. I won't even bother doing the angle chase, but this is the same angle, that's the same angle, and this is the same angle, and that's the same angle. Now, if you focus your attention on triangle XYZ, 3 angles which are congruent, so each of these angles better be 60 degrees, right? Similarly, if you focus your attention on triangle PQR, again 3 angles, all 3 are 60 degrees. Aha! So therefore, the conditions of the problem that we're given, let me just make it slightly larger, that angle A, C, and E are congruent to each other, and then B, D, and F are congruent to each other. What it implies is that we have 2 equilateral triangles which are somewhat rotated, or you can think of it as a spiral similarity if you want to. All right, so that's the picture that we have in the back of our mind. And at that point, there are numerous ways you can, well, attempt this problem. One way, which is the most direct way, no calculation whatsoever, is to directly construct the center of homotety, or, well, spiral similarity in this case, for this picture, right? And I'll just leave that solution to you as an exercise, but let me just give you a hint. The hint is to notice that quadrilateral BYQD is cyclic. So this is a cyclic quad, but in a similar way, DZRF is also cyclic. There you go. I think it's clear, right? Because those 2 angles are equal. And then similarly, this is equal as well. But then, guess what? We use Michel's theorem to easily establish that these 3 circles should have to go through that point there. Yeah, it's just a direct consequence of Michel's theorem. For instance, if you were to focus your attention on triangle P, Q, and R, we just selected 3 points on the 3 sides of that triangle PQR, namely the points B, F, and D. And then we did draw 2 of the circles, then necessarily the 3rd circle should also go through that point. And interestingly, yeah, one can show that this is an interesting point, a center of homotety, or homotety combined with rotation, so spiral similarity in a sense. I'm not going to do that. I will just do a direct solution using Viviani's theorem, right? So it will be very straightforward. I'll just use observation 1 and 2, and then boom. Well, okay, so the nice thing about the 3rd observation, it kind of helps us draw a nice, neat picture if you guys want. So that's exactly what I'm planning to do. So I start with an equilateral triangle, and all I do is I rotated it slightly to get yet another equilateral triangle. It's hard to rotate something nicely, so I'll just eyeball it to the best of my ability. Okay, so pretend it's something like this. Yeah, this doesn't look exactly like a well, actually it wasn't bad, I think. Anyhow, yeah, so well, now what we can do is I think we already labeled it. I can just use the same labeling if you guys want. So if you start out with a quadrilateral ABC, I'll try to be as explicit as possible so there's less confusion about the way I label vertices and so on. And I think between A and B I called it PQR, and the other one is XYZ. Okay, so this one was PQR. This is an equilateral triangle, so these are all 60-degree angles. But at the same time, I think I labeled this one as an X, Y, and this one is a Z. Now, interestingly, if you use Viviani's theorem, then we can get something interesting. So let's first start with the first with the hypothesis. So remember the thing that we are trying to prove, right? Prove that the intersection point of the angle bisector, the A, the C, and the E angles, angle bisectors, they meet at, say, P. Okay, so let's start with that. Well, okay, so let me first write the full statement. Then this implies that the remaining angle bisectors of B, D, and F, angle bisectors also meet, say, at at Q, for instance. All right, so that's what we plan to prove. So now we already know that these angles are congruent, so they're interior angles. They meet at this point P to begin with. All right, there you go. So this is my point, say P. To begin with, let me just directly apply the Viviani result to get something very interesting, actually. Let's use, which color can I use? I want to use orange, for instance. There you go. Orange sounds good. So I'm just going to drop perpendiculars to the three sides of, say, for instance, triangle XYZ. So I drop a perpendicular here. I drop a perpendicular there and here. And in fact, I'll just go ahead and label them as well, so there's less confusion. Say, for instance, that this is X1. That point here is X2, and this one is X3. Clearly, by the Viviani lemma, if you will, Px1 plus Px2 plus Px3 happens to be equal to the altitude of triangle of which one? XYZ. So the altitude of, if you will, triangle XYZ. Let's write this notation. Then let's see what happens next. Because P is such that it's where those angle bisectors meet. In fact, let's go ahead and label that as well. So these angles are both angle 1, you can call them. Well, actually, let's not give numbers. Let's instead give alpha, beta, and so on. Let's call these two as alpha. These two are beta, and then these two are, say, theta. Well, because those angles are both alpha, and by the first observation that I have just made, I might answer that. And going back to my orange color, there you go. Clearly, Px1 is equal to. So if I drop a perpendicular here and I label this as, say, y1, for instance, Px1 and Py1 are equal, right? I might just go ahead and replace the Px1 here with Py1 plus, well, Px2, on the other hand, if you focus on Px2, it's where the C angle bisector related to that. So if I drop a perpendicular to that side and I label this as y2, then clearly Px2 is equal to Py2. And lastly, Px3, because it's an angle bisector at E here, that's the way we defined the point P. And if I label this point as y3, that's just Py3. Hey, Py1 plus Py2 plus Py3 is the sum of the distances from that point P to the three sides of the equilateral triangle PQR. Aha! You guys see that? But that's just the altitude of triangle PQR. Wow, so what just happened is we have two equilateral triangles, so triangle XYZ and PQR. Not only by angle chasing we have proven that, but now using Viviani's theorem, we also are saying that these two triangles, equilateral triangles, are actually the same size. Do you guys see that? This is just the same size triangles. So wow, that's fantastic actually. All right, so as a result, so this implies, let's do the final touch, XYZ is congruent to triangle PQR. All right, now we can directly finish up the problem. Let's go back to a more reasonable color. All right, so now I will go ahead and start with two angle bisectors, namely the angle bisector of B and D, and let them meet at a point, say, Q. Let's have it. Okay, I want to distort the picture a little bit maybe because, all right, so suppose that Q is somewhere here, okay? So this angle, whatever, let's call it gamma, and then gamma there, and then these two angles, delta and delta, there you go. So let's call the intersection of the B and D angle bisectors as Q. Well, obviously they will meet at a point. Now, only thing remaining is to show that FQ is also an angle bisector as a result, right? And so let me write that down. Let BQ and well, DQ B correspond B angle bisector. Okay, B and B and D angle bisectors. Well, the angle signs are already there, so let me just call it bisectors respectively. Bisectors respectively. Well, show that. So the only thing remaining to finish the proof is to show that the F angle bisector also goes through that point. So show that FQ is an F bisector. That's it. Once we show that, we are done. But now you guys can already guess what I'm about to do next. Pretty much the same type of argument. From the point Q, I will drop some perpendiculars to the three sides. Let's use a more fancy color like purple. Okay, let's go ahead and start. So from the point P, let's drop a perpendicular to AB. So this is a 90-degree angle. And let me call it as, say, for instance, V1. And in a similar way, I can also, because I want to recalculate the altitude of triangle XYZ, which I already labeled it here. So that would be V1. So this is AB. Next one would be probably CD. I need to drop a perpendicular to side CD. There you go. I will label this one as maybe V2, I guess. And lastly, I need to drop a perpendicular to this one over there, and I will label it as V3. Clearly, QV1 plus QV2 plus QV3 is, well, from any random point inside this equilateral triangle XYZ. I dropped 3 perpendiculars to the 3 sides, so QV1 plus QV2 plus QV3 is necessarily the altitude of triangle XYZ. Again, the altitude of triangle XYZ can be written as QV1 plus QV2 plus QV3. But now, obviously, I can make use of the fact that Q is, by definition, on the intersection of the B and D angle bisectors. As a result, QV1, if I were to drop a perpendicular to BC here and label this one as what? Let's call it, for instance, U1, I guess. Yeah, why not? U1, let's call it. And, well, obviously QV1 and QU1 would be congruent, right? So I can just go ahead and replace QV1 with QU1 plus. Well, similarly, QV2, if I were to drop a perpendicular there, okay, so pretend this is perpendicular and let's call this U2, for instance. V2 is congruent to QU2. Why? Because we have angle bisectors here. QU2 plus, and then QV3, I can't do anything yet, right? Let's just leave it as, as QV3. But wait, earlier we suggested that, we suggested what? That if you look at the altitude of triangle PQR, it was given as such, right? So using the yeah, well, actually, we don't even need that. We can directly, okay, let's just directly look at from the point of view of triangle PQR. Right. So obviously that would be QU1, right? So QU1, so the altitude of triangle PQR using Viviani lemma again, that would be QU1 plus Q, I need a perpendicular to BC, which I did, or PQ, let's say QU1. I need a perpendicular to PR, which I can drop a perpendicular there. It will be extremely close to A, so somewhere here, let's say. Let's call this one as, say, U3. So QU3 plus QU2, right? So QU2, so those are the 3, right? So technically, this is supposed to be equal to QU1 plus QU2 plus QU3. Hey, do you guys see that? So as a result, what we have proven here is that, let me just do it here. The first terms match, the second terms match, so the third terms should also match. So QV3 is equal to QU3. But how did I define QV3? I just dropped a perpendicular from the point Q to the side EF. and dropping another perpendicular from the side, from point Q to the side AF. Now we are saying these two are equal. Well, the only way these two can be equal is if QF is indeed also an angle bisector, implying that QF is F angle bisector, F bisector. And that's it. That solves this really nice problem. Well, as a, I guess, as an educator, I guess I can give you an interesting problem, follow-up problem, which heavily uses Viviani's lemma again. I think the thing that solved this problem was this lemma, right? So the Viviani lemma. Another open problem, so maybe next week if I have time I can show you the solution to this one, open problem. It's an optimization problem. In any triangle, I think there is a certain restriction about the angles not being, I think the angles are supposed to be less than or equal to 120 degrees, otherwise it fails. I don't think that this statement that I'm about to make is correct. Well, actually, let me not make any statement. Let me not tell you which point works, but there exists a point inside triangle ABC which will minimize the sum of these distances to the vertices. All right, any triangle ABC where angles are, so this is an open problem, where each angle is less than or equal to 120 degrees, then you need to find the point P inside triangle ABC such that PA plus PB plus PC is minimum. Now it's kind of interesting when I gave you the hint, use Viviani, use Viviani lemma. It's kind of interesting that I'm saying use Viviani lemma because you would say, hey, look, the triangle ABC is not even an equilateral triangle, and Viviani lemma only works if the triangle is equilateral, and besides we need to drop all these perpendiculars and so on. But yeah, so you need to construct an equilateral triangle in this picture, so it's now up to you. See if you can make that construction. So it's a nice problem. I think this problem is sometimes also referred to as Steiner's problem. I don't think that's his main problem, but this was one of the problems that that Steiner has posed. All right, so if I have time, maybe next week or the week after that, I would like to share the solution to this optimization problem. All right, so that's it.